Hi and welcome. I'm the free internet guy, and in this one I'll be talking about little data, not the big data. Little data is back. In black, baby. I'll discuss charts and why even a little data can go a long way. Back in school, did you ever think, will I ever use this? I sure did. I was in math class and my teacher was talking about charts and numbers and tables. Meanwhile, I was thinking, why plot the data in the first place? How hard can it be to actually find the highest and the lowest number in a table? Lots of reasons exist why it would be hard enough for you to make a mistake. Partying? The big worries of life? Will the kids be okay? Will I get that new iPhone for my birthday? What time is the game on Saturday? She left me. Please end the war. And what's up with the Chinese? Plenty reasons. But I digress. While I was trying to save time and energy, I was missing the point. I was not even hitting the ball. Charts are way more than just the highs and lows and comparing numbers very fast. It's also about patterns, and even the simplest patterns can be near impossible to spot without a chart. Unless you are a mental math athlete that can do super fast calculations in your head, then in this case, this video is not for you. So move along, nothing to see here. Or maybe even a mental math athlete could miss the hidden patterns in the data. Let's take a deeper dive into the hidden life of little data on a chart. In this chart, I have plotted just 3 points. That's the little data. Let's zoom in. On the x-axis is the turn of the coil, and on the y-axis is the output of the coil in watts. I have added a trend line in the attempt to find the biggest deviation. The trend line is the straight fine blue line. The trend line only shows that every coil deviates. It even gives the impression that the middle coil, coil number 6, is the one deviating the most. So, after a lot of pondering, I got the idea to make a trend line for the first coil on the plot, even though it doesn't make a lot of sense from a statistical point of view. 1 point with 0 as its other reference point is not really a trend. It does, at least, show a slope, and assuming that if coil had 199 turns, it would have by far a lesser output than coil number 5. But just to make it fair, I did the same exercise with the 2 other points. What a mess. But it clearly showed that coil number 5 and number 6 were closer together slope-wise than coil number 3 was to any of the other 2 coils. Mission accomplished. But wait, there's more. Now, I only had to figure out why coil number 5 was so much better performing than the 2 other coils. Or why the 2 other coils were performing lesser than the coil number 5. The result I was expecting was that all the coils would have a more linear output than observed. I did some more testing. All showed similar results. I had the Faraday law of induction as a guide, but it wasn't until I looked into how transformers worked and I saw that the path or the length of the path of the magnetic loop actually mattered. The longer the distance that the magnetic field had to travel inside the iron core, the lesser the output. After looking at the coils, now with a fresh pair of eyes, it was quite obvious. The offset of the coil, the little distance from the tip of the iron core until where the coil actually sits on the iron core, mattered far more than I expected. Now, armed with this new knowledge, I started to make some new coils. One had a similar coil as coil number 3, but without the offset. The other one I made shorter, but with 4 layers instead of 2 layers. And I was right. The 2 coils performed far better than the original coil number 3. The result, however, showed that even though the coil performed 38% better, it wasn't quite on the trending line compared to coil number 5 with the 199 turns. But it is a start with very going good. It even suggested that using a thinner wire would naturally make the coils shorter and actually placed closer to the magnet.